Hi, this is Google Kickstart question, electricity. We have a number of nodes. Each node represents a junction, and the index for these nodes is from 1 to n. So in this example we have n equal to 5, which means that we have 5 nodes. These nodes are 1, 2, 3, 4, 5. And also we have n minus 1 edges. The first edge is between 1 and 3, and there is connection between 2 and 3, and 4 and 3. There is connection between 4 and 5. And each node has value represented in this vector. So node 1 has value 1, node 2 has value 2, node 3 has value 3, node 4 has value 4, node 5 has value 3. And if we provide one of the node with electricity, the electricity can move to the neighbors, or if the neighbor's value is less than the current node value. So if we provide electricity to node number 2, node number 2's neighbors is only 3, and 3 has value 3. 3 is greater than 2, so the electricity cannot move from 2 to 3. So only node 2 will have electricity, and so the number of nodes will be 1. If we provide the electricity to node number 5, node number 5's neighbors is node 4. Node 4 has value 4, which is greater than 3, and the electricity cannot move from node 5 to node 4, so the number of nodes is equal only 1, which is this node. If we provide node number 4 with electricity, so we have node number 4 has electricity. Its neighbors, first of all, this node number 5, which has value 3. 3 is less than this value 4, so the electricity can move from this node to this node. So we have node number 5 has electricity. The other neighbor is node number 3, which has value 3. 3 is less than 4, so the electricity can move to this node also. Now we keep going. At node 3 we have 2 neighbors. First neighbor is neighbor number 1, which has value 1. 1 is less than 3, and so the electricity can move to node 1. And also it can move to node number 2 because the value is less than 3. So in total we have 5 nodes if we provide node number 4 with electricity, and you can verify. It's verified there is this is the maximum number of nodes. If we provide one of these nodes with electricity, you can check only also for 1 and 2, and you will get a number of nodes less than 5. So the answer is the maximum, which is 5. And to calculate this value, we can do brute force solution by providing every node and using DFS algorithm to visit the neighbors that has value less than the current value, and stop if the neighbor value greater than current value. And we do this for every node, and at the end we return the maximum among all the answers. This solution time complexity is n square, so we need to find better solution. So the idea is, first of all, we need to create a vector of values and node indexes, pairs. So this vector will have and sort this vector. So the first item in this vector is the least value, which is 1, and this value is for node 1. So we have this pair, the first item. The second item is 2. Notice that it's sorted based on the value of the node. This is for node 2. Then we have value 3 for node 5. Then we have value 3 for node 3. Then we have value 4 for value 4 for node 4. Now we have this sorted vector, and sorting is based on the value. We have 1, 2, 3, 4. Then we need to iterate over this vector from left to right and calculate the number of nodes for every value, and store the result into a table. And we will be using this result in the next nodes that has greater value. So we'll start with node that has value 1, which is node 1. Node 1 neighbors is 3. 3 is has value greater than 1. So the value stays as 1. It means, and notice, like in the table, initially every entry has nodes number equal to 1. This is because this is the minimum number of nodes, which means that if we provide this node with electricity, this node for sure will have electricity. This is why we initialize every node by 1. And also notice that we skip this index because our indexing is from 1. So we create node, the table size is n plus 1, and we ignore the first entry. We start from we consider the values or the nodes after 1. As we said, we started with the node 1, and node 1 neighbor is 3. 3 has value greater than 1, so the electricity cannot travel here, so the value stay as 1. Then we move to value 2. Value 2 is for node 2. Node 2 neighbors 3. 3 has value 3, which is greater than 2, so the electricity cannot move here, and also we have only one node. Then we move to node 5, which has value 3. Node 5's neighbor is 4, and node 4 value is 4 greater than 3, so the electricity cannot move from 5 to 4, so node 5 has maximum number of one node. Then we move to the next node, which is 3, that has value 3. Node 3 neighbors, first of all, is 1. So 1 here, the value is less than 3, so the electricity can move from 3 to 1. So TB of 3, we added the value stored at TB of 1, which is 1. So here we add 1 come from this node, so we add plus 1, so this value becomes 2. The other neighbor for 3 is 2. 2 has value 2, which is less than 3, so the electricity can move from 3 to 2. So we need to add the result at node 2 to node 3. So here we have plus 1 and the value will be 3. The other neighbor for 3 is 4, but 4 has value greater than 3, so the electricity cannot move from 3 to 4. So this is our results for node 3. Now we move to the last node, which is 4. Node 4 has 2 neighbors. Node 5, which has value 3, and 3 is less than 4, so we add the results of node 5 to node 4. Node 5 value is 1, so we add 1 to this entry, COM2. The other neighbor is a 3, and 3 values 3 and 4 can move to the electricity can move from node 4 to node 3, and so we will add the results of at node 3 to node 4 plus, so the result here is a 3. We already calculated it, so 2 plus 3 equal to 5, and at the end we return the maximum of all of these values, and in this case it's 5. Notice when we calculated the results for 4, we have the result ready in a 3, so we don't need to go further. We just check for the neighbors, because we already calculated the results for the neighbors. And the time complexity for this is in log n, because we did the sorting at the beginning. Let's look at the implementation. Here we are just parsing the input, and we pass the edges or the connection vector n and a. A is the values, the vector that has the values, and here we created a graph, and for every node we push, like we insert the neighbors, so every node will has a list of neighbors, and here capacity represent this vector, so it's vector of pairs. The first value in the pair is the node value, then we have the node itself, the index of the node, then we do the sorting for this capacity vector, and we will iterate from over all the capacity pairs, starting from the first pair, and we check for all neighbors. If neighbor value less than the current node value, we accumulate or we add the neighbor calculated result to the node, to the entry in the table, and at the end we return the maximum of all the entries in the table.